dat is goed. Okay, welcome students. It's it's already 1:45 on a Tuesday, the 16th of March. Today is lecture number 5 in a whole series, 12 actually, a series of 12 on multibody dynamics B. The topic for today is the generalized coordinates, virtual power and D'Alembert forces, or in short, the TMT method. In the book it's chapter 13, and it has of course a close relation with last week's lecture, which was Lagrange's equations of motion, which is a very elegant way to derive equations of motion. However, with the TMT method you have more insight in what things are doing, and you can reduce the amount of work also, but especially the insight is important. Okay, so let's start with that. If all systems are go, and I see viewers, I see connections, I see recording, then let's kick off. Okay, our starting point again, of course, we start with not real power, but virtual power. Virtual power, oh, if I were a king, right? And then the virtual power in our case for this mechanical system is this virtual symbol. Power is a capital P. There's no index here, of course, because it's a scalar. So this guy goes away. It's just a number. Okay, so that virtual power equals, well, we have applied forces to the system, and then we take these D'Alembert forces, we subtract them. Then we have the total set of forces, then times the virtual velocities, because the product of force times velocity, force times velocity of the point of application of the force. I mean, there are so many hidden words in our things we describe. So the force times the virtual velocity of the point of application of that force, minus of course the inertial forces. And then that is for then we say it's in equilibrium, that's our statement, for all virtual velocities, as long as they're not zero, and fulfill the constraints. That is our statement. And we have to do something for that. Now, let's start by defining all our terms. So these FIs in our 2D mechanical system, and after the spring break, we're going to do 3D dynamics, but for now we have a collection of rigid bodies, and usually they are rigid bodies with inertia. Could also be that that we just have point masses, but for now we all have, then we only have an X and a Y force and no torque. But for inertial bodies with an extension, so it's a mass moment of inertia, Fx1, Fy1, M1, Fx2, and that goes on until Mn, if we have n number of bodies. Likewise, then these coordinates are x1, y1, phi1, x2, and it goes on to phi n. And then that guy is defined, that guy is defined. Now we have to define what is then this mass matrix, and in the two-dimensional case, it's this diagonal matrix with M1, M1, I1, M2, etc. until we have In. Okay, that having clearly defined, we now know what we're talking about. Now let's be specific again. Let's go to our example. So we have our inertial coordinate system, xy, the origin, and then we have one body, and we have a second body with some extension. And so this is body 1, this is body 2, and of course the xi center of mass coordinates, that's clear, those are here. So, and the number of coordinates we have here is 6, because we have two bodies, and 2 times 3 is 6, so we have 6. We have 4 constraints. Now, why do we have 4 constraints? Because we have 2 constraints here and 2 constraints here, right? Let's make a real constraint. So the conclusion is 6 minus 4, we have 2 degrees of freedom. So if we want to make we can choose two independent generalized coordinates. So it can be two independent generalized coordinates. And you're free to choose. Huh? Like in last week we can take anything. For now I'm going to choose this angle alpha with the x-axis, and here's also the absolute angle beta. So this one is parallel to this one. That's contrary to the homework from last week, where we had like for beta the relative angle. Now just as an elegant variation I will do the absolute angle. Meaning that our generalized coordinates in our case is this alpha beta, two-dimensional. Then of course with the Lagrange equations the next step was express your center of mass coordinates in your generalized coordinates qj. And I think we wrote that like xi is a function of qj. For now I want to be very specific that that is a set of functions we define. So I'm going to write it as xi is ti of qj. Now this is of course super confusing, because this t is not kinetic energy. Because kinetic energy is of course a scalar and we usually call it t, but the t stands for transformation. And yeah, unfortunately we only have 24 letters in the alphabet, in the Roman alphabet, and yeah, that's not enough, so we can get duplicates. But we have to live for now with that. So T stands for transformation, and Ti is we have as many transformation functions as we have coordinates as a function of this J and the generalized coordinates. Okay, so there was a thing in our equation, coordinates, although actually you don't see any coordinates. That's, by the way, super interesting. We need speeds and we need accelerations, right? So let's go there. So for velocities, what do? Super simple, we put a dot on top of it, then we take partial derivatives here, and well, since we all know what it's about, I immediately do the nice index notation with the summation convention, summation over j, and the comma for the partial derivatives. And of course virtual velocities, I mean there's nothing different between velocities and virtual velocities. Is just putting this magical symbol here. And again, it can be a delta here, it can be a v as a sub-index. It has nothing to do, absolutely nothing, Mr. Faulty. I know nothing with differentiation. Nothing. Okay. So those are the virtual velocities. Then what was the other thing which we needed in our expression? Accelerations, right? So again, differentiate this expression. X double dot I, or I should say accelerations. X double dot I equals, well, first I keep this constant and I differentiate that with respect to time, Tij q dot double dot j plus, and then I keep this constant and then differentiate this Ti. My mind is always quicker than my hand. Kl q dot k q dot l. Now for the real buffs in index notation, you will be surprised that, oh, here we had an index j and it's j again, but here we have suddenly k and l. What is happening? Well, I do that for clarity. It's not really necessary, but it ties these two together and it ties these two together. And we call this index, by the way, a dead index. It doesn't mean that it's dead and it's buried or whatever. With that we mean it doesn't come out of the equation. The outcome index is here, is an I, and within inside this is summation. And you can choose anything for that. You can take a J or K or L or Fietsbel or I don't know, anything. Mountain bike, any index. Now we have specific terms for that. This, which seems very complex, but the outcome is just one index. So we call that the convective term, and that's something I think from fluid dynamics. And it has things like alpha dot squared L, and it has V relative times alpha dot. Those kind of terms are there. And we're going to give it a special name. I usually like to call it HI equals TI K L Q dot K Q dot L. And that's, I do that to show, oh, it's just one vector, it's just a column, right? Okay. Now, by the way, we have introduced these generalized coordinates. So we have actually introduced new coordinates. We have introduced new coordinates, being those QJs, in our case alpha and beta. Meaning that we also have a set of new forces. So with these coordinates, you also have forces. Coordinates, we have forces. And we call those forces QJ. And what are they? That's the big question. Well, of course, they are tied together by the concept of power. So you could say power actually defines with QJ the meaning of these generalized forces. These are what we call generalized forces. Generalized forces. Now let's take a closer look. So we write that this power equals QJ, Q dot J, the sum over J, so it's the force times the velocity. But this is a general coordinate, so this is a generalized coordinate, so this is generalized force. And what do we mean by that? Well, let's take a look at that. We define QJ, right? Or we define, yeah, Q. Then we get a Q dot, and then power ties us to what is actually our generalized force. So that is the way. We have a coordinate, then we get a velocity, then we have the concept of power, and then we get the concept of the force. So how does that go? Well, if we have, for instance, an angle, then we have radians per second. Sorry, not radians per second. Then we have radians, right? And then alpha dot is radians per second. Then power is, of course, force times velocity, Newton meters per second. And that means that, of course, now I have to pull it a little bit to the right. Yeah. And this guy, I pull back again, I pull here, and this guy. Yeah. That means, of course, that if the product of this QJ and should be Newton meter per second, then the outcome is pen come back, Newton meter per second, and then we have to divide that by radians per second, or in other words, that's Newton meter. So the generalized force, which goes by a definition of an angle in radians, is a torque in Newton meters. And that's what you can envision. So likewise, if we have like a distance s, which is in meters, then our s dot is in meters per second. Of course, again, we have Newton meter per second. If we then do Newton meter per second and we divide that by meter per second, we get newtons. Meaning, if we have a distance defined as generalized coordinate, then the generalized force is just a generalized force is just a force. What if you define a thing like well, let's be crazy. Let's say we have something we call s squared, and that's meter squared. I mean, I don't know, some people do strange things, right? Then for the speed of this generalized coordinate, what do we get? Well, we get meter squared per second. But still, power is of course Newton meter per second, meaning that this Newton meter per second divided by this meter squared per second results in Newton per meter. Smells like a stiffness or something like that, but it just shows us that if we can define anything as a generalized coordinate, as long as it has a physical dimension, then power ties it to a generalized force, and it also has some dimension, and we can make a picture of that, like what we imagine by that, but in this case it's rather hard. Okay, so that about generalized forces. Let's get back to our equation. Now with these new or extra coordinates, being these generalized coordinates qj, we have these extra forces, q capital Qj, and we also have extra power, right? Meaning that we have to enlarge our virtual power expression. So in the end now we get delta P, and I put a star there, which is our original one, Mij, x double dot j, virtual velocities, I, and now we have to add the virtual power of these generalized forces. Yeah. And again, this is 0, for all velocities, as long as they're not 0. And you could also say, well, actually, for all these velocities which fulfill this transformation, because if all virtual velocities are according to this transformation, then everything is jiffy and all the constraints are fulfilled and the whole system stays together. It's like the glue, and it doesn't go apart. So all these virtual velocities should follow this transformation rule. We can substitute that, of course, and then here we're going to substitute what the accelerations are expressed in our degrees of freedom, and then finally we get the total expression. So let's do that. And the statement is then, of course, a system is in equilibrium. That is our statement, if that is the case. So let's start with the first part. So q double dot j equals, well, we have, of course, I want to get rid of this j, because that makes things, because I already have a j here, so maybe I'm going to call this k, right? Okay, so k, so x double dot k, to distinguish between the summation of a j here, because j's summation is over the number of degrees of freedom, and here the summation is upon the center of mass coordinates, and that's different. So I get tk, and then I use a j, that's okay, q double dot j, plus, and then I get my convective term tk, I have lm here, q dot l, q dot m. And of course, well, for shorthand we can use another term. Then the virtual velocities, these ones, right? I already have written it down, but let me repeat that here. Delta q dot j. So we're going to substitute this guy here and this guy there. And then we finally have everything expressed in our generalized degrees of freedom. So we get delta p star equals, we get our fi minus mik times, now I have to substitute this whole shebang, tkj q dot j plus tklm. Oh, klm, that's can fly away. Let's take care it doesn't fly away. Yeah, and then times, and now I have to substitute this times ti j delta q dot j, right? Plus, and then we have this other term, qj delta q dot j. 0 for all, and now we only have these variations, and as long as they're not 0. Well, if that is the case, then of course in the end you can take 1 0 0 0 0 1 0, and you get j equations. So you end up with J equations of motion. And how do they look like, these J equations of motion? Well, I'm going to reorder a little bit. So I'm going to put this in front of this expression. So I'm going to start with it Tij times, then we have the applied forces, minus, we have this Mik, and I'm going to just do the multiplication Tkj q double dot j, yeah. And I'm going to write here again, repeat this part times this. Oh, that's a minus then, of course. Yeah, it's a minus. Mik Tk Lm q dot L q dot M, convective terms, and then plus q dot J is 0. So these are my equations of motion. Of course, now I have to shuffle and reorder them a little bit, because eventually I want to have a mass matrix times accelerations, and on the right hand side I want to have forces. Well, I can do that. But before I do that, I want to define some shorthand. So I want to introduce these convective terms. Hk equals this Tk Lm q dot L q dot M. And with that introduction, I then can write down the first part. So I want to have the mass times acceleration. So that's this term times these guys. So Ti, j Mik Tk oh yeah, I should make an L out of this. I already have a J. Yep. L Q dot L. Okay, and then I put a bracket around this to note that, okay, these guys go together. And then all the other stuff I push to the right hand side. So what do I have to push? Well, these forces, of course, Qj are here. And then I get a term plus, and again this transformation, Tij, times my original forces, Fi, of course. And then, yeah, that's minus Mik Hk. It is shorthand notation for these convective terms. And this is in fact our result for today. Now you will understand why we call it the TMT method, TMT method. Why? Because the transformation Ti, j transforms the mass matrix, the COM mass matrix, to the, how do you say, degree of freedom, generalized coordinates, let's say generalized coordinates mass matrix, and therefore we call that a TMT. Now notice that this is a we can do a mixed notation. So if we now associate Tij with a matrix, Ti, j, so this is the index notation, and this is the matrix vector thing. So that's the thing which you do in MATLAB. Then the other index notation is Mij, and we're going to identify with a mass matrix with a column and a row. And what else do we have? Well, we have, of course, Fi, that's just a vector of forces. Qj, that's also just a vector of forces. And and therefore I wrote this actually, Hk, that's just a vector Hk. So now I have clearly defined from my index notation, what is it, low battery? From my index notation to my to my, what is it, I have to charge a little bit, 1 second, from my index notation to my vector notation. Okay, with that having said, now I can rewrite this equation into an equation where we have only matrix and vector terms, and that is sort of handy because that is what we eventually use in MATLAB, right? So then I'm going to write T transform, transpose times T, and I will get in a second why that's transpose. Vector Q double dot, oh, I haven't said that, but so Qj is of course a vector with this index. Yeah, and then equals, then I get my vector with the generalized forces, then T transform times the forces F minus M, and then the vector H. So this is like in a matrix vector notation, the whole thing. Okay, so why do I say a transform? And that is a bit of a tricky thing. More students usually have trouble with that. Well, the thing is as follows. If we look at this expression, we see MIK. So, and then you would like to associate the I and the K with row and column, right? Which I did here. Like it's a row and a column. So MIJ, I is the row, J is the column. Likewise TKL, with the K is a row and the L, so IJ is IJ, so row column. But notice what's here. It's also a TIJ, but if we see how the multiplication goes with the mass matrix, it's the row goes with the row. And that's not the way how matrix multiplication goes, because it's always the column index goes with the row index, like here. Meaning that we have to swap the row and the columns here, and swapping the row and the columns means in matrix and vector language means that you take the transpose of the thing. So T transpose MT times Q double dot is this. Then here we see again T transpose. Well, why? Well, there's an Fi here, and then the multiplication is Tij and not Tji. So therefore you have to do it. If you associate this matrix with this index thing, then you have to do the transpose here. So I get T transpose times the vector F minus M times convective forces. Of course, you can take one more step in this and you can say, oh, let's redefine some stuff. Let's say we call M bar is this T transpose times M times T, and let's call Q bar is this Q plus T transpose times F minus M H. And if I do it then like that, then how can I write my equations of motion? Well, I can write M bar times Q double dot equals Q bar. And that is beautiful because that totally complies with sum of the forces is mass times acceleration, our Newtonian mechanics. Because that's the only thing we are doing. We are doing Newtonian mechanics. We are doing sum of the forces mass times acceleration. Only we make it obscure by using other types of coordinates and interconnecting bodies instead of free bodies. So that makes it all a bit difficult. Okay, why this TMT story today? And why not just stick with Lagrange? Okay, now I have to go back to Lagrange to remember how did that work. So Lagrange, how did it work? Well, in Lagrange we used, of course, the Newtonian mechanics. So we used the sum of the forces minus the mass times acceleration. But then what did we do? We multiplied that with velocity and then with time, and then we integrated. Why? To get energy. What type of energy? Well, we had like here kinetic energy, E kinetic, and here E potential or so, and we called that T and we called that V. Anyway, that was the way. So you could say from Lagrange, well, anyway, we had these energy functions, T and V, which were in itself, of course, a function of Q and Q dot. This was from Q. Then how do we got our equations of motion? Well, then we had to do the following thing. take the time derivative of the kinetic energy with respect to the velocity minus kinetic energy with respect to the coordinate plus potential energy with respect to the coordinate is this applied force. And if you now rethink what you are doing, then actually you start with Newton, right? That's here. Then by integration you go up to the level of energy. And then by differentiation you go back again to the level of equation of motion. So it's like a rerouting of your, so hey, you go up and then you go down again. Now, I don't know how that is with you, but if you want to go from A to B, and there is also a straight route, instead of go up and then going down again, like a roller coaster, well, some like roller coasters, but I sort of get sick of roller coasters, so I want to have this straight route. So the straight route is actually the TMT method. Straight route is just Newton, Tij transformation, and then you get your equation of motion. So you don't have to go up to a level of energy, you just stay straight. So that's the TMT method. That's one of the advantages, and later on we will see more advantages actually. Okay, that was in a nutshell the theory of the whole thing. What is the time? Now we have time to do an example, right? So let's do an example. And to connect to the example from last week, I'm going to do again this pendulum on a card. So we had this support which we could move with respect to the wall, right? So we had like a distance s here. Of course we had a coordinate system, x and y, and it's inertial, and there's an origin here, say that's the wall, and suspended from that is a pendulum thing. And for now, let's take some rigid body, right? Something. So there's a CM here, center of mass, and there's gravity, of course, going on, and we have a length here to the CM, and I already named the coordinate here, and then I take as another generalized coordinate, for instance, alpha. What did I do? Yeah, alpha. Okay, so distance L, distance S. Okay, then the coordinates, the xi for the COM are in this case an x, a y, and a phi. I should define what is phi, right? And then so these are the COM coordinates. And then the generalized coordinates qj. Now, how many degrees of freedom do we have? No, the counting is actually super simple. We have 3 here, and there's one constraint, because this point, we haven't given it a name yet, but this point can only cannot move up and down, can only move left and right, meaning there's one constraint. So I end up with 2 degrees of freedom, and for now I choose to take this S and this alpha. So I have to express everything in this S and alpha. Associated, of course, with these xi's are, let's take this, COM coordinates, Associated with the xi are, of course, pen, go back. These forces Fi, which is Fx1, Fy1, and M1. And then associated with these guys, so we discussed that, those are these generalized forces. And apparently, since this is a displacement, a distance s, then this is going to be a force. And I sort of identify already from the example that it's like this force. This action-reaction force, Fs, working on this, and action-reaction, Fs. And then since this is an angle alpha, I identified that already as a torque. So there's apparently a torque working here on the body, M alpha, and that torque is counter working on the support, M alpha. So there's an M alpha. Okay. Yeah, we could say X, Y, and Phi for the COM. That having defined, for the TMT method, what do we have to do? That is the example now I'm going to do. Method. Well, we have to define this transformation. We have to define our coordinates in terms of these generalized coordinates. So I have to say xi is some ti of qj, which in our case is simple. It's x, this position of the center of mass x is this linear distance s, plus this L times, well, in this case it's sine alpha, right? Plus L sine alpha. Then the vertical coordinate y is, there's no s involved, it's just the angle alpha, minus L cosine alpha. And the angle phi is, well, if we start from the horizontal, then it's minus pi over 2 plus alpha, because the direction is, yeah, it's positive. This having said, and of course with our mass matrix, we need a mass matrix, but the Mij in our case is just a diagonal matrix, right, with M, and I. Or in other words, this matrix M, Mi, that's everything, all zeros here. Yeah, if those are the quantities, then, well, applied forces we have in our case, we have defined them, and in our case the applied forces, of course, if we only take gravity into account, no horizontal, only a vertical force, so no horizontal, vertical force from minus mg and no torque. And that with that in place, we can form our equations of motion. So we can write Tij, Mik, TKL, Q double dot L equals these generalized forces plus T Ij Fi minus Mik Hk. And Hk I will come back in a second. So we have all the elements in place here, right? Well, not really. We have defined the transformation. We need the Jacobian, but that's easy. If we look at our equations here, and we need to form the Jacobian, Tij, then it's just differentiation, right? So you have to differentiate these three first to s, that's our first coordinate. So to remember, I always write s on top of it, alpha, to know, oh yeah, that's differentiation with respect to that one. So with respect to s is a 1, and with respect to alpha, that's L cosine alpha. The second one, there is no s, there is an alpha, and it's a cosine, so cosine is minus sine, so it's plus L sine alpha. And the last one, there's no s, and there's a constant, but the constant goes away, of course, and then the alpha, that's a 1. The applied forces I already had, well, I can repeat them here in a vector form, 0 minus mg 0. Yeah, what is Qj? You could say, well, for now 0, 0, and no extra forces. You could do, but for now, no extra forces. Applied. No applied extra forces. Okay, next step. Now we have to form our accelerations, of course, our q double dot. I is Tik q double dot k plus, and then we get this TKLM q dot L q dot M. Well, this first part is already there because that's this transformation which you already have. Now we can focus on the second part. Yeah, and how you do the second part, there are a zillion ways. You could say, well, I multiply this with the speed s, and then I differentiate to the coordinates and times this speed. That's exactly the way you should go. So you said hk is a, so I have to take this term, which is in fact s dot plus L alpha dot L cosine alpha, and I have to differentiate that with respect to, well, our coordinates s and alpha, and then multiply with s dot and alpha dot. That is the way to go, and you have to do that for all three terms. Oops. So let's do that. There is a there's a s dot, and differentiate with respect to s. It doesn't add up, right? So maybe it's good. Maybe I go a bit too fast here. Maybe it's good to write down the speed again. Oops. X dot, what was it? S dot plus alpha dot L cosine alpha. Y dot is just alpha dot L sine alpha. And then phi dot is just alpha dot, right? Now for these convective terms, I only have to differentiate with respect to the coordinate and then times the speed of the coordinate. So the hk then becomes, well, for the first part, with respect to s, there is no s in the equation, so that's 0, right? Then with respect to alpha, yes, there is a alpha there, and so we get what is the alpha here? Cosine alpha. So the derivative of cosine alpha is minus, so we get minus L sine alpha alpha dot squared, right? Then again, for the second one, there is no s, so nothing to differentiate. There is an alpha, again sine alpha, differentiate, we get cosine alpha, so we get that's a plus, yeah, cosine alpha alpha dot squared. And the last one, there is no s, and there's also no alpha, so that's 0. So these are the convective terms. And a very smart mouse already sees as, oh, it looks a little bit like omega squared L, like centrifugal acceleration. Anyway, we will see that in a second. Now everything is in place, actually. So the first step we can do, this Tij, Mik, Tkl, we can form. And let's repeat that then again. So we write this transformation matrix: 1 L cosine alpha, 0 L sine alpha, 0 1, and then we have to take the transformation times M Mi. And yes, I take the long ride by doing this by hand to show you really what the work is about. And of course, in the end, we're going to do it with the computer, right? 0 1. So if we do that, then, in a quick way you could see, oh, this diagonal term only multiplies everything here. So the first with m, the second with m, and the last with I, and I can immediately take this multiplication thing. So then I can immediately say, oh yeah, that's true. But maybe you like the long route, where we say, no, we don't take very shortcuts. So it's m, and this is ml cosine alpha, and this is 0, and this is ml sine alpha, and this is 0, and this is I, just the diagonal multiplication with these guys. And then the final outcome of this is, of course, a matrix, which is okay. I have to write a little bit the matrix. So we have to transpose, so it's this times this, so that's an m. This guy times this guy, so that's ml cosine alpha. Then this guy times this guy, that's also ml cosine alpha, and then this times this guy, that's I plus ml squared with cosine squared, sine squared plus cosine squared, plus that's of course 1. So this is then finally our mass matrix. Next step is, of course, that we take that we have to form this right hand side. So again we have this transformation matrix. So before I do that, let me repeat. So what I'm going to do is I'm going to do the T, the right hand side of the equation. Let's get that in our mind. So that was Tij times Fi minus Mik Hk. So again I form this transformation here, sine 0, transform times the Fi is 0 minus Mg 0, and then minus, and then again this mass matrix. And do you remember what the convective terms were? Yeah, minus L alpha dot squared, what was it? Sine alpha, L alpha dot squared cosine alpha, and we had a 0 here. Okay, well that's actually super simple. The first part is of course this times this is 0. And then this times this guy is minus mgl, what is it, sine alpha. Okay, minus, and then this guy times this guy, again of course only a mass multiplication, so we can do, immediately can do these guys, so that's a 1, 0, 0 times this, so we get minus ml alpha dot squared sine alpha, and then this guy times this guy. Oops, that's a lot. So that's minus L squared alpha dot squared sine alpha cosine alpha, and then plus L squared alpha dot squared cosine alpha sine alpha. Oh, hey, they go away. That's nice. P. So remains, of course, minus minus is ml alpha dot squared sine alpha, and here we get minus mgl sine alpha. So now we have all the ingredients actually. So let's put our equation of motion together, right? We have the mass matrix, we have the accelerations. Oh, I see it's time. I will continue until 2:45, then do 5-minute break, and then do questions and answers, right? Okay, so mass matrix ml cosine alpha, ml cosine alpha, and then here we have I plus ml squared. Then here we get a s double dot, alpha double dot, and then here on the right hand side we have, for although it's 0, I like to write mfs there, because then we can easily discuss m alpha dot squared sine alpha, and then here m alpha, the dual, actually we call it a dual with the alpha, and then minus mgl, that's also a sine alpha. Okay, let's now focus on this equation of motion. And let's first talk a little bit while my pen is charging again. So how correct is this? That's always good if you have an answer to check. Well, do I agree with that? And maybe it's sort of helpful to put that picture of the system there, and we do a very simplistic sketch now. So we have here this mass bulb thing, right? We have this mg here. We have here this alpha, and we have this distance s. And for the rest, I'm not going to draw anything. Oh yeah, no, that should suffice. Okay, so the first equation of motion has something to do with the linear acceleration, the linear motion. Oh, what I'm going to write, I should write there's a mass and there's an inertia here. Okay, so the first equation is about the linear motion, right? So it's s doubled, it's about s double dot, about fs. So it's about the motion. So you could say I freeze the angle here for now, and the configuration and maybe also the speed will come in a second. And then what? Let's focus on the left-hand part. What mass do I? Oh, yeah, now it's moving. What mass do I feel when this guy is moving? Only in a linear way. So s double dot. Well, the mass I feel is m. If you freeze everything and if you move back and forth this, then it's, yeah, you just feel the mass. Nothing more, nothing less. That single mass. So that's the M term. Then here you will say, oh yeah, but there in this linear motion there's also a contribution of the alpha dot. Well, why is that? Well, of course, if we have an acceleration alpha double dot, then you could say, oh, there is an acceleration here, a linear acceleration alpha double dot L. And how does that contribute to our linear motion? Well, then you have to project that on the horizontal. So apparently with the angle alpha, I get only part of that. I get L cosine alpha, alpha dot squared, times mass. So that is, if there is an angular acceleration, in the linear forces, I feel this part. So you could translate it like that. Well, likewise, we go the other way around. If you then have an angular motion, then if I have an angular motion here, what do I feel? Well, around this point, there's this mass times distance, or this was the distance L squared, ml squared. So the mass moment of inertia about this point, this I, is ml squared plus point P. Plus this I at the center of mass. So that is the inertia which you feel here, mass times distance plus the inertia at the COM. So that's what you feel here for the angular acceleration. But if there's then also a linear acceleration, then that linear acceleration, only part of that, that S double dot, if you would draw the S double dot here, so then part of that S double dot also contributes to this angular acceleration. So therefore you have this ml cosine alpha. And see how nice symmetric it is. Isn't that beautiful? Okay, so that is the mass matrix explained. Then the other part, now on the right hand side, why do we have these forces here? Maybe I have to draw a new figure here. So again, I have my Fs, I have my S here, I have my Eps thing here. I have gravity here, mg, and this is the angle alpha. So now we're going to look at these forces. Well, we already said Fs is this linear force, right? And then we see a contribution ml alpha dot squared sine alpha. Well, what is ml alpha dot squared? Well, apparently there is, of course, a centrifugal acceleration, ml alpha dot squared, and times the mass, that's also an inertia force, right? And then we only have to take the projection of that one. So this small part contributes to our force. And of course it's with the minus sign, with D'Alembert, with the inertia force are minus m times x double dot. So therefore we have a plus sign here. So in the linear motion we feel this angular motion in that sense. And what is here? What is going on here? Well, for the rotational part, gravity, what is doing gravity? Well, part of the gravity is only contribution. What part of the gravity is contributing? Only this part of the gravity. This times arm. This L, distance L, times this force. We have to take the torque, and then it's the projection of that one. So that's the mgl. And of course the torque is opposite the angle alpha. It's like this. So therefore we have the minus sign. So in a nutshell we have explained what's going on. Now I like to go back, because here we saw sine alpha and so on. And initially we didn't have that. So who is putting in all this sine and cosine? That's this transformation. So you could say that this transformation is a projection of the COM forces. It projects these forces. And how does it project? Because the coordinates there are, the generalized coordinates are a nonlinear mapping of these to the COM coordinates. And that makes this projection. And it makes exactly the right projection to get exactly the right equations of motion. Okay, that was actually what I wanted to talk about today. And I propose looking at the clock. So we have 14, so we do Q and 8. We resume with the Q and 8 at 14:45. In Zoom. So you can do now a very, very short break, short coffee break, maybe, coffee break, and then we do this Zoom. Yeah, how do I do that? Well, because then I first stop the recording. I don't stop the streaming, but I start the zoom and I show that we are in the zoom. Where are we? Where am I? Yeah, I have to start the zoom. Where am I? Zoom. This is the zoom. Yeah, for sure. Okay, launch the meeting. And connecting. Ja, dat gaat ook goed. En I'm gonna share my screen. Ja. I'm gonna share server screen. Share. Ja, dat is oké. Oké. I'm sharing the right screen. Yeah. That should work. Okay. I'm coming into